Hello everyone, and welcome to today's chem lesson. Today, we are going to talk about intermolecular forces, which are the forces that work between two separate molecules. So far, we've been talking about bonds, and how bonds are formed, what they're made, what they do, but bonds are inside of a molecule. They are intramolecular forces. Today we want to take a step back and look at two different molecules, or two of the same molecules, and see what connects multiple molecules together. Those connections, the ones that connect 5 water molecules together, or the water molecules to the sugar that you put in when you make tea, those forces are called intermolecular forces. They hold multiple molecules together, and there are 3 different types. There are dispersion forces, dipole-dipole forces, and hydrogen bonding. Hydrogen bonding is a little bit of a misnomer. It is not an actual bond, it is a type of intermolecular force. We're going to go through and we're going to talk about each of these type of intermolecular forces, starting from the weakest, which is dispersion forces, and working our way up in strength until we get to hydrogen bonding, which is the strongest force. First up is our dispersion forces. Dispersion forces are the forces of attraction that exist between molecules at their most basic. Every molecule, no matter what it is, has dispersion forces. Molecules that are nonpolar, molecules that are symmetrical, have only this type of intermolecular force. And we'll see why as we go a little further into this lesson. Imagine it's gym class, and you have to take a volleyball to play with from the bin. This volleyball down here at the bottom, the one that I'm coloring in red, is your favorite because it is your favorite color. If you are first at the bin and you have to take this volleyball out, you need to dig through all of the volleyballs above it before you can get to the one on the bottom that you want to play with. The force that you feel pushing down on this volleyball is a dispersion force. There's no actual attraction between these volleyballs. They're not magnets. They're not glued together. The only force that exists between these volleyballs is the force of them pushing down on each other. That is a dispersion force. We're looking at a force that isn't attractive, right? It's not magnetic, it's not glue, it's not adhesive. It's just pressure from multiple things being stacked on top of one another. Dispersion forces get stronger as the size and mass of the molecules increase. If these weren't volleyballs and were instead bowling balls, and the same situation applied, right? This one's your favorite and you want this one, you have to dig through all of the other bowling balls before you can get to this one on the bottom. It's much harder to dig through the bowling balls than it is to dig through the volleyballs, because the bowling balls are heavier and they're pushing down on this one that you want with more force. Right, so as these molecules get heavier, the dispersion forces get stronger. As the molecules get bigger, the dispersion forces also get stronger. Right? The bigger and heavier they are, the stronger the dispersion forces are. Let's look at a practice problem. The strongest dispersion forces exist between molecules of F2, I2, Cl2, or Br2. Here, when we're looking at this, each of these molecules is the same size, right? Each one is something 2. Size isn't going to play a difference, right? Size isn't going to be a factor here. But mass will play a factor, right? And the heaviest of the bunch here is iodine. And we can tell that by looking at the periodic table. If we pull up the periodic table, we would see that F, Cl, Br, I go down the table in this order, with masses increasing as you go. Right? So the heaviest one, right? This is our bowling ball compared to volleyballs and ping pong balls. Right? The heaviest one is going to have the strongest dispersion forces. Dispersion forces aren't our only type of intermolecular force. We also have dipole-dipole interactions. Now, these are our medium strength force, and these occur in polar molecules. Right, when a molecule is polar, right, let's look at this from the picture here. When a polar molecule exists, the electrons get bunched up around one spot. In this case, if we look at it, the electrons get bunched up around this oxygen. That means that there is an unequal distribution of electrons, right? If we think back to our previous lesson, this cake has icing that is very unevenly distributed. Right, and this big pile of icing is around the oxygen in this case. This means that the oxygen is sort of negative. Not fully negative. It hasn't taken electrons. It's not an ionic bond. It has not stolen or transferred electrons to itself. But if we look at the sharing of electrons that's occurring, it is uneven in favor of the oxygen. So the oxygen has more of those electrons. Right, that gives this bit of the oxygen a sort of negative charge. And the rest gets a sort of positive charge. Right, because of lack of electrons. Again, they haven't fully been taken away, but they're not being equally shared, and so it creates this imbalance. And what this imbalance leads to is the fact that now we've got a negative piece and a positive piece. So in addition to the dispersion forces, in addition to the fact that these molecules are pushing down on each other, stacked one on top of the other, there is also this magnetic attraction. Which means if I have this molecule paired up with another of this molecule, we're going to end up with a sort of negative spot attracted to a sort of positive spot, creating a literal magnetic attraction. And we're going to see that happen as we propagate this picture outwards, right? If I were going to draw another one, I would put an O over here and draw the rest of the molecule around that. I see this O over here, so I would put an H over here and draw the rest of the molecule around that. And this creates these little attractions that are not bonds, but make these things stuck together a little stronger. So this makes it even more difficult to pull apart these molecules. Because not only are they stacked one on top of each other, not only do they have dispersion forces, they also have dipole-dipole interactions. They also have this magnetic attraction between them. When we look at hydrogen bonding, which is our strongest type of intermolecular force, we are looking at the same exact thing. We are still looking at a dipole-dipole force. We're just looking at the strongest three examples of a dipole-dipole force. And the strongest three examples are going to be H connected to F, H connected to O, and H connected to N. Those three bonds are the least fair in their sharing of electrons. These three bonds, instead of having something where like H to H is a 50-50 split, these three bonds over here are like a 10-90 split. The closest thing we can get to being ionic, to being a full transfer of electrons, without actually being a transfer of electrons. Right? Technically, this is still sharing, even if the ratio that they are sharing at is not a even or fair or good ratio. So it's the same exact principle. It's still this magnetic attraction here between a sort of positive and a sort of negative. But it's the strongest possible example of that. And so, if I have a molecule and I want to try to figure out what kind of intermolecular forces it has, I can actually figure that out by asking two questions, and two questions alone. And they are, first, is the molecule polar? A non-polar molecule has only dispersion forces. And that will give you your answer, right? Something like a CH4. Something like H2. Non-polar molecules have only dispersion forces because there is no magnetic dipole within the molecule. There is no spot where the electrons bunch up and cause this sort of negative, which can then lead to attraction. If the molecule is polar, we can ask one more question to differentiate between dipole-dipole and hydrogen bonding. And that question is, does it have H connected to F, O, or N? If it does, a polar molecule with one of these bonds has all three types of intermolecular forces: dispersion forces, dipole-dipole forces, and hydrogen bonding. A polar molecule without one of these three bonds has only dispersion forces and dipole-dipole forces. So something like NH3, which is polar and it does have H connected to N, fits this category. So does water. So does HF, hydrogen fluoride. But over here, something like chloroform is polar, but does not have HF, HO, or HN. And so this is somewhere in the middle, right? Dispersion and dipole-dipole. These two have the weakest type of intermolecular force, just dispersion forces. And these three have some of the strongest intermolecular forces, with all three of them. Let's do a couple more practice problems. Which of these molecules has only dispersion forces? Which of these molecules has only dispersion forces? To solve this, we need to find something that is non-polar, which means we're looking for lines of symmetry. HF has one line of symmetry, and that makes it polar. CH4 has multiple lines of symmetry, that makes it non-polar. But before we choose this as our answer, we should check our third option, which only has one line of symmetry, making it polar, solidifying our answer as choice 2, the only one of the bunch that is non-polar. Because the kind of molecule that has only dispersion forces are non-polar kinds. What about this one? Which molecule has dipole-dipole interactions? And again, I'll draw them up for you. Right, which one of these molecules has dipole-dipole interactions? Here again, polarity is going to be the key. Dipole-dipole interactions tells us it must be a polar molecule, because there needs to be a uneven distribution of charge. F2 has two lines of symmetry, which makes it non-polar. CH4, we just looked at before, has 4 lines of symmetry, making it non-polar. Ethanol over here has 0 lines of symmetry. There's no place in here I can draw a line of symmetry, making it polar and also solidifying it as our answer. Right? A polar molecule has dipole-dipole interactions. One more. which of these things has hydrogen bonding? Which of these things has hydrogen bonding? For hydrogen bonding, we are looking for two things now. We're looking for something that is polar and has H connected to F, H connected to O, or H connected to N. In this case, we can figure out which one it is without checking polarity. Here, my H's are connected to C's. That's not O, F, or N. Here our H's are connected to C's. That's not F, O, or N. But here we have H connected to F. This must be our choice for hydrogen bonding. And it is. Now, intermolecular forces actually play a huge role in day-to-day life. We can use intermolecular forces to explain why certain things have different melting points, different boiling points, different vapor pressures. Strong intermolecular forces lead to higher melting points, higher boiling points, and lower vapor pressures. And this is because the molecules are held together very strongly. So it's hard to separate them. Something with weak intermolecular forces, we have the opposite effect, right? Lower melting points, lower boiling points, higher vapor pressures. Because there's not a lot holding these molecules together, and so it is easy to separate them from each other. Right? With stronger intermolecular forces, it takes more energy to force things apart. But with weaker intermolecular forces, you can force things apart pretty easily. You can melt them, you can boil them pretty easily. With that, I am going to transition us over to our Google Meet for questions, comments, concerns, and attendance, and I will see you there.